bring your kids to work day. And so I took them. So my kids are the ones on the extremes, on the left and the right, on the right side picture. And they came to my undergraduate graph theory course. This was in spring semester, which is in a more advanced graph theory course taken by the students who actually want to be in the class. And so they were in the first row, as you can see on the left. And then later on, they participated. If you've taken the graph theory course and you've done the 5-color theorem proof and so on, you can recognize some of the scribblings over there. And I'll save it to the end so on their notebooks, they show what notes they took during that class. So I'll save it to the end to show you what they wrote, what they learned that day. So graph theory is the study of graphs, which are abstract models of networks, and you can represent them on a piece of paper by drawing the vertices as dots, and the edges as segments or curves connecting those dots. But they can be studied from a linear algebraic perspective, and to do that, you can represent these graphs, these dots and lines, as matrices first. And so there are various matrices that one can associate to a graph. One of the most common ones is the adjacency matrix, and this is the one that I'll focus on today, in which if your graph has n vertices labeled in a certain way, in this matrix, we have the rows and the columns indexed by those vertices. So if on my picture, I would put here 1, 2, 3, 4, 5. So here I would have the vertex 1, and then I will have 2, 3, 4, 5, and then 2, 3, 4, 5. And that's you represent the rows and the columns with these labeling of the vertices, and then in the entries of the matrix, in the position xy, you write down the number of edges between x and y. So 2 and 3 are adjacent, so that corresponds to this entry of 1. But 2 and 4 here, they're not adjacent, so that corresponds with this entry of 0. There are 0 edges. Now, the graphs that I'll talk about are undirected. So the matrix that this adjacency matrix will be symmetric and it will be real, and therefore the eigenvalues of A will be real, and we will have n eigenvalues, including the multiplicity. This follows from our linear algebra courses. Now, one can ask what happens if we label the vertices in a different way. Instead of labeling the vertex in the middle 1, in the center 1, and labeling by a different number, what happens to the matrix? And yes, you will get a different matrix, but regardless, like if you change the labeling of the vertices, the matrices will be similar to each other, and the eigenvalues will always be the same. So you can regard this set of eigenvalues as an invariant of the graph, and it doesn't depend on the labeling that you give to the vertices. Now, spectral graph theory, what it does, it plays a ping pong game between, like many areas of mathematics, between different parts of mathematics. So it plays a ping pong game between combinatorial properties of graphs and linear algebraic properties of the graphs. So, for example, if a graph is connected, and let's say it's deregular, so deregular means just every vertex has the same number of neighbors, which is d. So you have 2 examples at the bottom. Then in that situation, one can prove that the largest eigenvalue of the graph equals d, and all the eigenvalues of the graph are going to be contained between minus d and d. Now, this part here, to show that d is an eigenvalue, is not too hard, because if you take the adjacency matrix and you multiply it by the all 1 vector, then what you collect on the other side is the row sums of the adjacency matrix, and because the graph is deregular, it will be d, which is d times 1. So that proves that d is an eigenvalue. To show that d is the largest is not too hard, and similarly, to show that it's between all the eigenvalues are between minus d and d is not that much difficult. Another property of the graph that combinatorial property that can be explained in terms of algebra, or is equivalent to a spectral property of the adjacency matrix, is that if the graph is deregular, then the graph is bipartite if and only if the smallest eigenvalue is minus d, and this is actually also equivalent to the entire spectrum being symmetric with respect to 0. So when the graph is bipartite, what you see on the positive side of eigenvalues, you're going to see on the negative side with a minus, with a sign change. So I give you some small examples there. Here you have the complete graph K5. You have 5 vertices adjacent to each other, all the adjacency present, and each vertex has degree 4. So it's 4 is the largest eigenvalue with multiplicity 1 because the graph is connected. And it's not too hard to show that minus 1 is the smallest eigenvalue multiplicity 4. And over here you have K33, in which you have this complete bipartite graph with 3 vertices on each side. And it's also, in this case, it's regular, so 3 is the largest eigenvalue. And then it's symmetric with respect to 0, so you have 3, 0, and minus 3 as eigenvalues. Now, with this in mind, let's go to a problem that doesn't, at the first glance, doesn't have anything to do with eigenvalues. So this is a question in the 60s, and this is called Moore bound because Moore observed this upper bound. That let's say you want to build this communication network, and you have 2 constraints. So the first constraint is that you have every node has exactly d neighbors. And the second constraint, so this is that every node has d neighbors. And the second constraint is that you have diameter 2. And diameter 2 means that if you have 2 nodes, they are either adjacent, or if they're not adjacent, then if they're not adjacent, then they have at least one common neighbor. So you can get from one to the other at least in 1 step or in 2 steps. Okay. And the question is, okay, what's the largest network that you can build with these properties? And Moore observed that the upper bound, the upper bound is d squared plus 1. And to see that, you basically, what's the largest number of nodes that you can have? You have a vertex. It has d neighbors, which are at this level. So you have 1 neighbor here. Then you have d neighbors here. And what's the largest number of neighbors that you can have at the next level over here? Well, each of the blue neighbors could have d minus 1 on the next level. And so the largest number of neighbors that you could have is if all these neighbors are distinct. So in total, you end up with this 1 plus d times d minus 1, which adds up to d squared plus 1. So that's an upper bound, because that doesn't mean that such a network necessarily exists, because the big question is, how in the world are you going to connect these neighbors here, these vertices at the bottom, such that the degree of each of them is d and the diameter is still 2? So that's the question. I mean, this picture shows that everything may be okay from the perspective of this vertex on the top, but it may not be okay from the perspective of a purple vertex and so on. So that's the question. And this was answered by Hoffman and Singleton in the 60s. And they proved this beautiful result that says that if you have a deregular graph with diameter 2 and d squared plus 1 vertices, then d has to be one of these values. So it looks like some kind of alchemy, or, you know, like these numbers, you can try to wrap your head on where they're coming from. So I wrote in red there, what's the proof? So their proof is essentially assume that you have such a graph with d squared plus 1 vertices, deregular in diameter 2. Then they look at the adjacency matrix of the graph, and they prove that the adjacency matrix of the graph has 3 distinct eigenvalues. It's d because the graph is deregular and is connected, and 2 others, which are the conjugates roots of a quadratic equation, and they can be expressed in terms of d. And then they determine the multiplicities of these eigenvalues in terms of d. And every multiplicity has to be an integer. And if you unwrap what that means, you end up with some divisibility condition that lead to D being one of the possible values 2, 3, and 7 or 57. Now, for D equals 2, there is such a graph and it's unique, and that's the cycle on 5 vertices. 2 squared plus 1 is 5. For D equals 3, there is such a graph and it's unique, and it's a graph here. This is the Peterson graph, so this is the graph over here. And when D equals 7, Hoffman and Singleton constructed such a graph. Here's a pictorial kind of idea of the construction. I think this is due to Neil Robertson, but there are various ways to construct these graphs. So you can build it this way from a bunch of cycles of length 5 by connecting them in a certain way. And in that case, you have a graph on 50 vertices with 7 regular and diameter 2. Now, the big question in this area is what happens with D equals 57. And nobody knows. So in that nobody knows if such a graph exists or if it doesn't. In that case, in case you want to calculate, you can go to your calculator. D squared plus 1 is 3,250. And computer search, it's not going to work. And for this question, I know people that believe the answer is yes, and just we haven't been able to construct it. And I know people that believe the answer is no, and I tend to side with the people that say no, because what happens is for D equals 2, 3, and 7, all the constructions that we have are very symmetric graphs, like all their vertex transitives, so all vertices look alike. But when D equals 57, there are results that prove that the symmetry group, the automorphism group of these graphs, is going to be very small compared to the order of the graph. So if such a graph exists, it's going to have to be quite ugly, and you can think that that's going to be hard to be achieved. Now, you can study this problem by replacing this condition about diameter 2 to a larger diameter. So you can ask the same question: what's the largest graph that you can construct in which you have diameter 3, which in the graph is deregular? And you can do a similar like a more bound works in that situation. You can go 3 levels instead of 2 as before, and you can get an upper bound given by the number of vertices in a certain tree. But in 73, independently, Banai and Ito and Damerel proved that there will be no graph attaining equality in that case, which has degree 3 or more. For degree 2, you can get an odd cycle to get to equality, but for degree 3 or more, there are no such graphs. And again, this I don't know a combinatorial proof of this result. Both the results of Hoffman and Singleton and Banaito and Damerel, they use linear algebra, namely study this hypothetical graph, investigate its eigenvalues, and say something about the multiplicities of its eigenvalues being integers. And from there, you either get a contradiction or you get this 2, 3, 7, and 57. Now, let's move to another question. And this is one of my favorite problems, the one I give all the undergraduates that come and say they like math, because I know it's appealing and they can prove results on it fairly quickly. So this is a quote from an interview with Henry Pollack. So Ron Graham and Henry Pollack worked at Bell Labs in the 70s, and their boss was J.R. Pierce. And they were talking about some system of data transmission. So Graham and Pollack wrote actually 2 papers on this subject in the 70s. They're online and you can read them. So this is some quote about this system of data transmission. So what is this system of data transmission? Well, so the idea is that you have this network or this graph, and you want to label the vertices by words over some alphabet of the same length, such that if you pick 2 vertices, you can tell what is the shortest path between them, and you can tell how you can how you can go on such a shortest path efficiently. So on this example, let's say I have the vertex 0, 0 here, and I have, this is the three-dimensional cube, obviously, and you have the vertices are binary words. They're already, from the definition, they're labeled by this by words over the binary alphabet 0 and 1, with the property that they're adjacent if and only if the distance between them is 1. The number of positions where they differ is exactly 1. So if I want to go from 0, 0, 0 to 1, 1, 1, first thing I see is that the distance between them, the number of positions in which one has a 0, the other has a 1, is 3. And then in order to find the shortest path, I can move from 0, 0 to a vertex where this Hamming distance is decreased. So you move there, and the Hamming distance is 2, and you move here. The Hamming distance is 1 between this vertex and the target, and then you move there. Now the problem is, so this works fine on these graphs, but there are other graphs on which you will have a problem, and this is the smallest example, the triangle, in which you will have a problem with this labeling, because you can label this vertex with 0, this one with 1, and then what do you put here? And maybe you say, okay, let's use more larger alphabet. You can do a 0 here, a 0 here, but it's still it's a problem on this vertex. And now what Graham and Pollack realized is that they could get away with just introducing one more symbol, which they call, I don't think they call star. It has a different letter in their papers, but let's just call it star for now. And this star, the intuition is that this star can be at the same time as a 0 as a 1. So now what they proved is that for any graph, there exists such a function f from the vertex set. So you can label the vertices with words over the alphabet 0, 1 star of the same length k, such that for some sufficiently large k, that's an important issue, such that the distance in the graph, so this is the dg of xy, this is the length of a shortest path between x and y in the graph, equals the number of positions in which the label of one vertex, so the number of position j in which the label of one vertex has a 0 and the label of the other vertex has a 1, and vice versa. So if you look at the example on the right, this is a complete graph on 6 vertices. It's clear that this is satisfied if I take this one, it's like 4 zeros and a 1 at the end, and then all zeros, because the j in that case is 5. That's where you have one different entry. But if you look, for example, what happens between the same vertex 0, 0, 0 and 1 star, then in this situation, the j equals 1. That's the only j that is counted, where the zeros have a 0 in the first entry, the second vertex has a 1 in the second entry, and then the stars can be anything. So that's basically the addressing scheme that they came up with, and you can actually figure out how to do this triangle in this scheme. So before you couldn't do it with 0. So I have this triangle. Let's say I have a 1, 0, and I have a 0 here. And now what do I do on the other vertex here? I can do a 1 here. I can do a star in the first position. I can do a 1 in the second position. And one way you can think of this is, what happens here is that I took a cycle on 4 vertices in which I had a 0, 0 and a 1, 0 here. And in this cycle on 4 vertices, like a 2-dimensional cube, I have a 1, 1 and a 0, 1. And what happened is that these 2 vertices here, I squashed them into one vertex. So I kept the 1 on the second coordinates because there was a 1 here and there was a 1 here. And the other 2 coordinates, I kind of squashed them into a star, which can be at the same time a 0 as a 1. So what they proved, and I'll show you how this works on the second slide, on the next slide. Graham and Pollack proved that there is always a sufficiently large K for which this works. And here's a question that it's interesting, is to determine the smallest such value of K. And this is an open question to the best of my knowledge, to figure out if this determining this n of g is NP-hard or not. I believe it should be, but there hasn't been any reduction from to show that it's NP-hard. Now, why does this parameter exist? And well, essentially, this addressing problem is equivalent to a decomposition of a multigraph into a certain kinds of subgraphs, which are called bicyclics. So first of all, what decomposition of one multigraph? Well, we start with our graph G, and then we get the multigraph D of G, which has the same vertex set as G. So on that picture, this is G, and this is its distance multigraph. And whenever you look at two vertices X and Y, let's say this is X and this is Y, and in G, the distance between them is 2. So therefore, in the distance multigraph, I put two edges between them. Now, for the other vertices, if I have this vertex X and if I have this vertex Z here, the distance between them in the graph is 1. So I just keep one edge and so on. So that's how you construct the distance multigraph. And it's easy to see, for example, that if I have Kn, then the distance multigraph of the complete graph on n vertices, it's the same as Kn because all the vertices are adjacent to each other. Okay. And now one can prove, I'm not going to do here, so this is actually a result, but it's not very difficult, this part here, that an addressing of length K of a graph is equivalent to a partition of the edge set of the distance multigraph into, so that you have a length K here and you have a K here, into complete bipartite subgraphs, or also called bicyclics. So a bicyclic, I give you different examples there, is just complete bipartite subgraphs. So you have some vertices on the left, some on the right, and they're all pairwise adjacent to each other. Now, one thing this implies is that there are always going to be some addressing, because if you look at just a single edge, if I have a single edge, this is a bicyclic, because this is a complete bipartite subgraph K11, one vertex on the left, one on the right. So if I take any of these distance multigraphs, I can always partition it into bicyclics. Now, of course, the question of partitioning to the smallest number is a different one, but you can always partition it. So you can always have this addressing of length K. Now, so that's a construction. So that's how you get upper bounds on this parameter n of g. What about lower bounds? And the lower bounds come from linear algebra. So this is where, again, the eigenvalues play a part. And this is a theorem that Graham and Pollack attributed to Witzenhausen. It says that if you have a graph with distance multigraph, or so here I'm going to identify the multigraph with its distance matrix. So let's say this is G. Let's label 1, 2, 3. Then the distance multigraph is going to be this one, 1, 2, 3, and then in my notation, this is the same thing as, so I have a 0, I have a 1, I have a 2, and then I have a 1, I have a 1. So this is what I mean here when we talk about the number of positive and negative eigenvalues of this matrix. And now, yeah, this is also it requires a proof, and it's a beautiful result. And essentially, the key to it is the fact that if you look at this distance multigraph matrix, it can be written in a certain form. It can be written as xy transpose plus yx transpose, where x is a tall matrix with n rows and k columns, and also y is the same, like a tall matrix, And these are the characteristic vectors of the biclics that are used in the previous decomposition. So I won't give you the details. You can find this in Baba and Frankel, Linear Algebra Methods in Combinatorics, and in Brouwer and Hammer's book on spectral graph theory and so on. Now, so what application does this result have? Well, if you take the complete graph on n vertices, then like I mentioned before, this distance multigraph, it's the same as the graph itself. You know the eigenvalues. So in this situation, the number of positive eigenvalues is 1, and the number of negative, including multiplicity, is n minus 1. So the lower bound from this construction is at least n minus 1. And there are actually many partitions of the complete graph into n minus 1 biclics. There's actually an exercise in Baba and Frankel about that. And this is what is called the Graham-Pollack theorem, and it has some other, the proofs are all essentially linear algebra. There's a proof by Tverberg, which phrases it as solutions of linear systems and so on, but they're all, everything is linear algebra in my opinion. Now, in around the same time when they proved this result, so in the same paper actually, Graham and Pollack proved this upper bound for the n of g. It's a general upper bound that this length of the addressing is at most the diameter times n minus 1. And later, Ron Graham conjectured that the upper bound from there can be improved to n minus 1. And that was proved by Peter Winkler in 1983. This is called the Graham squashed cube conjecture. The squashed cube, because of what I showed you earlier of how you squash the vertices of the cube. And this one, you can find the proof of it, in Winkler's original paper, but it's also chapter 9 in Van Lint and Wilson course in combinatorics. They give you the detail with how Winkler used breadth first search and depth first search to come up with an addressing of a length n minus 1 for any graph. Okay, so any graph, you can the length of its the minimum length of its addressing is at most n minus 1, but maybe graphs can use fewer symbols. So like I said, I gave this question to the undergraduates because you can tell them what the problem is, and you can give them small graphs, and they can try to find the optimal addressing. So we wrote a paper a while ago with some collaborators, and Michelle Markevitz. She was an undergraduate at University of Delaware, and she now works at NSA. And we addressed various graph products in distance regular graphs, and the one of them was Hamming graphs. So in the Hamming graphs, you have the vertex set is a generalization of the cubes. The vertex set is a set of words. So you have words of the form x1, x2, xd, and all these entries xj come from an alphabet of q, and cardinality of q is q. So if q is 2, then it's the cube, and you have 2 of them adjacent if and only if they differ in exactly 1 position. So over here you have 2 pictures of H23. So H23 is the one on the left, and here you have everything adjacent if it's in the same row or if it's in the same column. So that's essentially the same as this graph. And we found out optimal addressing of this graph of like one. You construct the addressing of this length d times q minus 1. So that's construction. And then to show that they're optimal, there's nothing smaller. We use the eigenvalue result, and you can calculate these graphs are distance regular, so they have a lot of regularity in them, and you can calculate the distance matrix spectrum. And that has, so here I have eigenvalues on the first row, and their multiplicity is on the second row. So you have 1 positive eigenvalue, so you get this number here, and we have 1 negative eigenvalue for the distance matrix with multiplicity dq minus 1, and that matches our upper bound, and that's how we got the result. Okay, so we did Hamming graphs in that paper. We also looked at the Johnson graphs. So Johnson graphs, they're also a class of graphs that are well studied, and we have k subsets of a set with an element intersection adjacent if intersection is size k-1. This is J52. This is the first. It's a complement of the Peterson graph, and we so the eigenvalue bound gives us n-1, but we improved it and we got n. And that was pretty much the progress at that time. And later on, I had another undergraduate student, Brendan Gilbert, and I gave him this problem with Johnson graphs. And he wrote a computer program to look for, do some backtrack algorithm to look for this addressing. And later on, he reverse engineered the program to actually theoretically describe the scheme of addressing, and I help him prove that the upper bound for j and k is k times n-k. So we got the upper bound of k times n-k by an explicit addressing for all these graphs, and it's sharp for k equals 1, because in that case you get n-1, and j and 1 is the complete graph, and it's sharp for a small range. That's as far as our computers can get us, k equals 2, n equals 4, 5, 6. But it's not sharp for k equals 3 and n equals 6. Brendan Mackay actually found an addressing of length 8. So in the same paper, we looked at other questions. So we did some computation. So using Brendan's program, we did some computation for this n of g, and we noticed that it's for this value of n of g is not n-1 for most of the graphs. It actually tends to move away from n-1. And this is an argument that Noga alone did, basically to prove that for a random graph g n 1/2, most of the graphs will have n of g at most n minus some constant times log of n. So this is an open problem. So we don't know what's n of g is when g is a random graph. So this seems a difficult problem. You have this upper bound of n minus 2 minus 1 log on this side, and the best lower bound comes from eigenvalues, and it's about n over 2. So there's a big gap there. So here's the open question. This is not known. This is a very simple graph. It's a cocktail party graph. The situation, you have these n couples, and no person wants to talk to their partner at the dinner table. So you have this. So the graph is basically the complement of a perfect matching in a graph. So you have all these edges that are missing here and so on. And to address this graph, Zaks proved the upper bounds here, and proved also a lower bound of m plus 1. And later on, Alan Hoffman in 2001 improved the upper bound from m plus 1 to m plus square root of 2m. But it's a big gap between these two things. So what happens here is that the lower bound, when you use the eigenvalues, the distance multigraph has many zeros in the spectrum. So this maximum of m plus and n minus is far from the construction, and nobody knows what to do. Okay. So since it's breakfast, let's talk a little bit about some pancake graphs. So this is I'll change the topic. This is this question that was studied by Bill Gates when he was an undergraduate, which is you have a stack of pancakes. You wake up in the morning and perhaps they're not in the right order. And what's the minimum number of flips that you can flip them to the right order? And he proved these bounds that are here in red, lower bound and upper bound. And later on, people improved them to this green and to this blue. But this is an open question. What is the diameter of this pancake graph? Now, this pancake graph, you can think of it in terms of permutation. So you can think of vertices as being permutations, as you see on the right. And what you do is two vertices are adjacent. Like for example, from 1, 2, 3, 4, I can go to 3, 2, 1, 4 because when I have 1, 2, 3, 4, I can flip the first the prefix and it becomes 3, 2, 1, 4. And so from 3, 2, 1, 4, I can go here to 2, 1, 3, 1, 2, 3, 4. I can go there because I can flip the 1, 2, and I get 2, 1, 3, 4, and so on. Now, this graph has been studied. It's a very symmetric graph and so on. So it has n factorial vertices, and it's n minus 1 regular. And it's actually a Cayley graph. If you don't know what that is, don't worry about it. But it's a symmetric graph, and Cesi using group representation and Chung and Tobin using equitable partitions, they proved that the second eigenvalue, which is a parameter important to many things, is n minus 2. Now, I did some work with Zhao Kuang Tang, who is an undergraduate at NTU, who visited me in 2019 for 6 months. So we studied this problem. So this is a picture taken in 2019 in the fall. So that's me. This is Noga Alon, who was giving a colloquium here at UD, and you see on the blackboard, we talked to him about all our problems, and he couldn't solve them right away. So we were quite happy. And this is my other undergraduate, Brandon Gilbert. So we talked about all the problems. Now with Zhao Kuang Tang, so this is Zhao Kuang Tang, we looked at flip graphs on perfect matchings. So here, you flip something. So what you flip is, if you take a perfect matching and the neighbor of it, you pick two edges. Let's say I pick these two edges, and I replace them either by these blue edges or I replace them by these red edges. So you get a graph, and this has been studied from different angles. So from the random walk perspective by Diaconis and Holmes, combinatorially from Hernando, Hurtado, and Noye, and also combinatorially by these other authors. And this is a picture of the graph when n equals 3. So you have all the perfect matchings. There are 15 vertices here of perfect matchings of K6. And they prove a bunch of things, chromatic number of the perfect matching of K and N. And they had this conjecture that seems interesting. The chromatic number of this graph is n plus 1. And they prove it by computer for n equals 2, 3, and 4. And we work on it, and it's not easy actually to when you deal with a chromatic number. And so the upper bound, the best upper bound they could come up with is 4n minus 4 using this one of the complete bipartite graphs. And in this work with Gordon Royal and Zhao Kuang Tang, we can improve it to half, so we can get an upper bound. And this is an algebraic proof. You embed these vertices into some finite field, the smallest finite field that can have them, and then if your perfect matching is of this form, you color that perfect matching with this with this function where this f is the injection into that field. And when you flip, only two entries from that coloring have changed, and so when you subtract the coloring, you get the product of two non-zero entries, and in a field it has to be non-zero. Now we did some computation. So Gordon Royal is a master of mathematics and computational mathematics. So we have this work on GitHub, and these graphs grow very fast. So n equals 5, you have already 900 vertices. N equals 6, 10,000. But he actually found coloring with the right value. But we don't know if the chromatic number of these graphs is actually greater or equal to 6, or if the chromatic number of here, we don't know if equality happens. So finding lower bounds on the chromatic number is actually, it's quite tricky. So these are open questions. So maybe some of you can think about them. When we studied this problem, one graph popped into our study, and this is a sign reversal graph, SRK. And here the vertices are sign permutations. So you have a vertex that it could be something of the form -1, 5, -2, 3, 4. So that's a vertex. And adjacency is basically you take some sub-interval, like for example this one, and you flip it. So this vertex will be adjacent to -1 stays the same, but now you will have a -3, you'll have a 2, you'll have a -5, and you'll have a 4. So this graph is also quite symmetric, and we did some work on it, and we observed that k choose 2 seems to be the second eigenvalue. So we try to prove something similar to Cesi and Chung and Tobin, and we can prove that. So we check this conjecture for k less or equal to 5. We actually prove that k choose 2 is always an eigenvalue, but so that implies this inequality. But we couldn't prove that lambda 2 is at most k choose 2. So we have this conjecture that I think it's interesting, and but we don't know how to do it. Okay, so let me quickly tell you about a few more things. I don't think I'll go through the slides. I had a big plan, but so one is about a place where eigenvalues have been used with great success, which is the theory of expander graphs. So the notion of expansion of a graph is the following. You go over all subsets of vertices, like here you have 3 vertices in A, and you count this parameter here, E of A and partial of A, counts the number of edges that go between A and its exterior. So you count all these edges and you divide by the number of vertices in A. So, and you take A to be at most half of the number of vertices. So this is called the expansion constant of a graph. And people study expanders. An expander is a graph in which this parameter is large compared to 0. So you want it to be as large as you can. Now, when you talk about expanders, there are 2 things. So there are 2 properties that they have, informally speaking. So sparse. So that means that think about a a degree of regularity, D, and think about an infinite family of deregular graphs with a number of vertices growing large. Okay, so that's sparse because the number of edges is linear in the number of vertices. And the other property can be expressed in 3 different languages. So in combinatorics, algebraic, and probabilistic, and they're all equivalent to each other. And combinatorics is basically that H of these graphs is bounded away from 0. So not greater or equal to 0, but bounded away from 0. So if you take the sequence of these graphs, the expansion constant is bounded away from 0. Algebraic is that the spectral gap d minus lambda 2 is bounded away from 0. And probabilistic is that the random walk on the graph mixes fast. Now, on this picture here, this graph here from the picture looks like it's not an expander because you have bottlenecks. Like you can break it into 2 parts by removing just 2 edges, and you cut it into 2 big parts. Now, this graph on the right, it's hard to say from the picture. So the easiest way to do is to look at the eigenvalues. Now, in the 80s, this was made precise, but by these results of Alan Millman, Tanner, Mohar, Chigger, and so on. And it basically, the way you should regard this result is that it says that H of G is bounded away from 0 if and only if d minus lambda 2 is bounded away from 0. Okay, so then the question becomes, this parameter H of G is actually difficult to compute. So it's NP hard or co-NP hard, I forgot, but it's difficult to compute. But the eigenvalues are easier. So the question is, what happens is you try to construct graphs which have small lambda 2. How small can lambda 2 be? Well, this is Alon Bopanay and Serre, and which says that basically square root of d minus 1 is the best you can hope for. And this result led to this introduction of Ramanujan graphs. So you have this notion of connected irregular graph is Ramanujan if and only if all the eigenvalues are between minus square root of d minus 1 and square root of d minus 1. So this was introduced in this paper by Lubotsky, Phillips, and Sarnak, which is called Ramanujan Graphs. It's in Combinatorica in '86, and independently by Margulis. And Lubotsky, Phillips, and Sarnak have this explicit construction of infinite families of deregular Ramanujan graphs when d minus 1 is a prime power. And this uses some work of Ramanujan from, it's related to a conjecture of Ramanujan about the number of ways you can write the natural numbers as a sum of 4 squares and so on. And for the longest time, nobody knew what happens when d minus 1 is not a prime power. And recently, this is the breakthrough result of Margus, Spielmann, and Srivastava recently, I guess 6 years have gone since then. And they proved that there is an infinite family of deregular graphs with the second eigenvalue at most 2 square root of d minus 1. And there is an infinite family of deregular bipartite Ramanujan graphs. And the key to their proofs is the result 1, which is that any deregular graph has a sign adjacency matrix with largest eigenvalue at most d2 square root of d minus 1. Now, what is that? So you're given any, you're taking any deregular graph, and so you could take, for example, the simplest one like this, and you have the adjacency matrix, and it says that you can flip, you can change some of these ones to minus ones, like this, such that the largest eigenvalue is at most what you want. And so that's their big result. So it uses this notion of sign adjacency matrix, which is very important and appears in the study of equiangular lines, for which you have an expert at NTU in Gary Greaves and so on. But it's been used also. So this is my last few slides. This notion of sign adjacency matrix have been used to disprove of sensitivity conjecture that was proved by Hao Huang a few years ago. And this sensitivity conjecture is a conjecture in computer science about the sensitivity of some Boolean functions, but it can be rephrased as a question about hypercubes. If you take at least half of the number of vertices in the hypercube, there will always be one vertex which is adjacent to at least square root of n other vertices. And this square root of n is sharp. It was known from the 80s in this paper by these big names, Chang, Fury, Graham, and Seymour. And Hao Huang is a professor at Emory, proved this result and proved this conjecture. And this is a short paper in the Annals of Math that everybody should know in combinatorics. And the proof was summarized by Ryan O'Donnell in a tweet. And essentially, there are a few steps, and it's linear algebraic. It basically, you can find a sign adjacency matrix of this graph that has square root of n and minus square root of n as eigenvalues with multiplicities 2 to n minus 1. And then you use Cauchy interlacing, but you can do it with bare hands. You don't, just some dimension argument to prove that the largest eigenvalue of the subgraph is bigger than, greater or equal than square root of n. But in any graph, the valency, the largest degree, always beats the maximum eigenvalue, and you're done. So that's the proof. So I had some other things to talk to you about. My time is up, so I can go straight to my. Let me see how I can do that. I can go straight to my last slides, my punchlines. So these were the slides of my kids. So when they, the notes of my kids. So on the left, it's the younger one. He wrote Euler's formula. You can see it here, E equals V plus F minus 2, some other things. And the older son, he wrote also, he put his name on it for color theory and so on. Every map can be colored with for colors and all this stuff. So this is my last slide now. So thank you very much for your attention. And I'm happy to take any questions that you may have.
Thank you, Sebi, for your interesting talk. We do have some time for questions. If you have any questions, you can click on the raise hand button and wait to be called upon, or you can type your questions in the chat. Okay, maybe I'll go first, Sebi.
Yeah.
I'm very interested in the matching polynomial of graphs. And from what I know, they have used the fact that the largest roots of the matching polynomial of deregular graphs is 2 times square root b minus 1 in the recent results regarding Ramanujan graphs. So I've been wondering about what are the connections between roots of matching polynomials and eigenvalues of graphs, and I don't seem to find much information on this topic.
Yeah, I mean, I don't know much more than you do. So the way I see it is, you have this. So what they, what they did is that, and this was known before them, is that if you take all these signings, you're given a graph which is deregular, and you take all the signings of the adjacency matrix of this graph, and you take their characteristic polynomial, and when you average their characteristic polynomials, amazingly, you get the matching polynomial of that graph. And that was known, I think, to Gottsiel and Goodman in the 80s. But now, just because some polynomials average to another polynomial, it doesn't say much about their roots. I mean, in this situation, you know that the roots of the matching polynomial are real, and they're most 2 square root of d minus 1. And the easiest proof is this one from Gottsiel with this path tree situation. And then you have the situation with they invented this new method involving interlacing polynomials to show that the conclusion that I said, that there is one signing that is going to do what you want it to do, namely that the largest root of it is going to be less than or equal than the largest root of this matching polynomial, which by Hellman and Lieb and so on is at most 2 square root of d minus 1. But yeah, I don't know that that part has been pushed more. I mean, of course, for trees, matching polynomials are the same as characteristic polynomials. I don't know of any other breakthrough results in involving matching polynomials and the spectrum.
Right. Thanks, Abby.
Yeah.
We have one questions from. Okay, we have Han Mao, who raised his hand. So Han Mao, you want to ask a question?
Yeah. Okay.
Hey, sorry. Hi. Hey. Nice talk.
Thank you.
Sorry. Let me put my. Oh yeah. Okay. Yeah. Basically, I put in the chat also.
Yeah, I saw the question in the chat. Yeah. I don't know what happens for p less than a half. I mean, you should try to do the. I haven't thought about it. I talked to some people who are like experts in random graphs, and it's a tricky question because it is a tricky question. With p less than 1/2, you can try to mimic the upper bound that from our paper, which is from p equals 1/2, about the construction over there. But for lower bound, so lower bound is like for p equals 1/2, you get this semicircle law and so on for this eigenvalue of random matrices. And I'm sure there are other results for other, for the other matrices of, but you have to be careful what happens when p is less than 1/2, because the distance matrix may be different, because when p equals 1/2, almost surely the random graph has diameter 2. So the distance matrix is just adjacency matrix plus twice the adjacency matrix of the complement. But the gaps are, I'm guessing that the gaps are going to be big, but I think it's worth looking into it. But I don't know if anybody has done it.
I see. Okay, thank you.
You're welcome.
So in general, when P is less than half, do you think the number will decrease with n, or will
Yeah,
it still be? Because
I had
the Hamming graph, it was very small, it was long n.
It's tricky because like people like Alon, Bachman, and other people in random graphs, Fan Chang and so on, Xing Peng, they looked at the biclic partition of the random graph.
Okay.
But this and in that situation, there's something from Erdős that like you can always partition the edges into stars by taking the complement of an independent set. Like a vertex cover. A vertex cover you can do, and that's pretty much close to that. That's where it is for, I think, for random graphs. But addressing is a biclic decomposition, but it's not of the graph itself, it's of this distance multigraph. So when you get distance multigraph, I think Xing Peng explained it to me once, is that not everything is random. In the distance multigraph, you have, like, for example, when p equals 1/2, it's distance multigraph is essentially a random graph on which you put a complete graph on top of it.
Okay. Yeah,
and
so
that it seems to mess up all the situation there.
Okay. Yeah. Thank you. Okay.
You're welcome.
Any more questions?
Oh, Gary.
So Gary has a question. Hamming
Gary.
graphs. Yeah, I mean, so yeah, that's a good question. So Graham and Pollack did cycles. So for even cycles, optimal length is half of the length. For odd cycles is 1 minus the order. They did trees. So for trees, you have this result of Graham and Lovas about the determinant of the distance matrix of any tree has this very nice formula, n times 2 to the n minus 1 and so on. So that implies that you get n minus 1. I think Graham and Pollack did complete bipartite graphs with a few exceptions, but I think those were done by, I think, some Japanese authors in 2008. And with the undergraduate, Brandon Gilbert, we try to do even complete three-partite graphs. And you can almost do all of them, but you have some small cases in some cases in which you are caught between two values, like your eigenvalue bound says x and your construction says x plus 1. And yeah, it's not so obvious. So then we did the the Hamming and some of the Johnson, but Johnson, there are still many of them that are not known.
Oh, so for three-partite, did you give up hope, or
no, I still have the student to work on it, but now he's so Brandon, when I did this work, he was an undergraduate, and now he started PhD here, and he's taking courses and so on. So I'm kind of work on it, and then yeah. So I can send you the stuff that we did. We have some families where we
are
caught between two values. Yeah, I mean, it's the other thing is this thing about proving that is NP hard. I mean, if you decompose a graph into the smallest number of biclics, that's NP hard to do it. But in this situation, you're doing the distance multigraph, and I asked Noga Alon about it, and he said, yeah, it should be NP hard, but nobody has found, you have to find the reduction, and nobody has done that. So that might be worth doing.
Okay. I think we are almost out of time. Okay, if there are no questions, I guess we shall end our session here today. Thank you everyone for joining the session today. On behalf of the organizer, I'd like to thank Sebi again for taking out his time to do this wonderful presentation for us. Okay, we shall end our session here today, and you may proceed to exit the meeting. Thank you, guys.
Thank you, Cheng. Thank you, everyone.